In this video, we're going to look at phase changes, more specifically the phase changes that occur between gases, liquids, and solids. On page 342 of your text, you can see and find this in other places also, the various terms that are used to describe the phase changes that occur. You're going to see terms like freezing and melting, condensation. You're also going to see terms you may not recognize, like sublimation or deposition. Now, one that is curiously missing is boiling. Now, why is boiling not listed there? Because I thought that's what happens when a liquid changes to a gas. In reality, it's not boiling. Boiling is something else that we'll talk about. So you got to kind of become familiar with those terms because we will be revisiting those throughout the next couple sections. All right, so concept we want to talk about first is what's called equilibrium vapor pressure. And this is kind of going to lead into what the heck is boiling. Specifically, this talks about liquids and gases. What this will help to determine is what is the concept of boiling, when does boiling occur? To do that, we need to know what the structure is, the molar mass, as well as the effusion rate. Meaning, how quickly does a gas move? All three of those factors are going to play into this. Now, think of a couple terms here. You hear the term volatile or non-volatile. Well, volatile, again, is something that the explosive situation can change rapidly, and so on and so forth. In terms of chemistry, volatile means a chemical that has a low equilibrium vapor pressure, which basically means it evaporates very quickly. Non-volatile has a high EVP and evaporates slowly. Imagine that you put gasoline, pour some on the driveway, and then you pour some water on the driveway. You're going to see that gasoline evaporate a lot quicker on the driveway. In your house, you could do something like rubbing alcohol and water. If you pour that out on your table, that rubbing alcohol will evaporate a lot quicker. You could even, again, sometimes you may notice if you put rubbing alcohol on your skin, things like that. If you clean something, it feels like your skin is drying out. It's because it's evaporating very quickly. So what's happening here? Well, imagine you got two containers. One has water in it. The other has gasoline. You put a lid on it and you close it up. The blue circles represent gas particles that are being generated. If you notice in the example of the gasoline, there's a lot more gas particles present than there is in water. So the gasoline is changing into a gas more rapidly. Now some people say, wait a second, how does that deal with low EVP? Because you would think that means there's not a lot of gas because there's not a lot of pressure buildup. It's actually the opposite. What low EVP means is it has a very low pressure, therefore it's very easy for it to change from a gas to a liquid. It allows it easy. Low P, easy, liquid to gas. High pressure, it's difficult liquid gas. Give you an example. Say you're playing with your brother or sister and you're mad at them, and you want to sort of hold them down on the ground and not move them. Again, you may have already done this to some of your brothers or sisters, or you may want to. But imagine their water, okay, and they're trying to get up. They're trying to escape, evaporate, whatever you want to call it, boil. But your air pressure, you're kind of pushing down on them. So in water, it's very difficult for water to overcome what's pushing against it. Okay, so your brother or sister's the water, you're that EVP. In gasoline, it's kind of the opposite. Imagine your little brother or sister trying to hold you down. It's very easily for you to get up. Imagine your gasoline. It's very easy for you to get up and escape, okay, evaporate, boil, how terms you want to use, because there's less pressure pushing on you. Now that concept right there is really, really important because that leads into why things boil when they do. So let's revisit that boiling a little bit here. We get to boiling. High altitude, low altitudes, and maybe you know something about that a little bit here. So here's when something technically boils, when the equilibrium vapor pressure is greater than or equal to atmospheric pressure. So imagine if that gas is able to push away and spread out, then it's going to boil. If it's not able to push out or push away or escape, that means the atmosphere is holding it down. Now, let's take altitude. Low altitude, high atmospheric pressure. High altitude, low atmospheric pressure. When we hear the phrase high altitude, it's low atmospheric pressure, sometimes I feel the air is thin. What do we mean by the air is thin? Less dense. Well, what is less dense? This means less oxygen density. Oxygen is not as dense. It's harder to breathe. Why is it harder to breathe? Air's thinner. So why is the air thinner? When you take in a breath, you're not getting the same amount of oxygen as you would at a lower altitude. A lot of you have heard about, high altitude training. Athletes train at high altitudes. Why is that? They're depriving their body of oxygen for the purpose of training their body to be more efficient in converting that oxygen and using it in your heart, in your lungs, in your blood, transfer, all that stuff. So when they train in high altitudes, then they go back to low altitudes. Their body has been conditioned to work harder. Now in the presence of more oxygen, it's easier. It's like lifting a whole bunch of heavy weight, every so often, and then have to go to some type of competition where you got to lift the lightweight, and you're just being able to lift as, a lot. You've also heard of the terms hyperbolic chambers. Those are chambers with low atmospheric pressure. Right? So that phenomenon leads to the situation where we can actually make water boil at a temperature lower than 100 degrees Celsius. Why is that? The atmosphere is not pushing down as much in a high altitude. So that allows the water to evaporate faster or sooner. Whereas in low altitude, not as quickly. If you set up the right conditions, you can actually get water to boil at a temperature less than 100 degrees Celsius. We normally see it as boiling at 100. That's when it does its cooking. What did we just say there? Boiling's got absolutely nothing to do with temperature. Not a thing. It's all about the pressure. You've seen in class, or will see in class, do the demonstration of I can make just tap water straight out of the sink, boil. If I put it in a vacuum and I'm removing the air pressure, if there is nothing holding it down, then it can escape. Imagine this is like a can of M&Ms. One can I seal, and the other can I don't. And I shake the M&Ms. The can that's sealed, the M&Ms aren't going anywhere. If I shake this can of M&Ms, then it's going to go all over the place. Okay, so you imagine I'm shaking it. They're going all over the place. They're going to fly all over. That's the same principle as why something boils. Okay? Again, we can talk about it more in different chemicals and do they do that like water does. All right. Next little concept we're going to talk about is how this kind of ties into energy, because we can change temperatures, and changing those temperatures can affect certain reactions. So now what we're going to do is imagine we're in a sealed container, and A and B is liquid and gas. So here's what happens is if I take liquid and add heat to it, okay, I then can change it into a vapor. How do we know that? Well, liquid has less kinetic energy than a gas does. Okay? Gas has higher kinetic energy. So if I put more energy into a liquid by heating it up, I can turn it into a gas. That is technically considered an endothermic reaction. At the same time, I can take a gas, and if I take away heat, if I cool it, I'm going to remove kinetic energy from it. It can turn back into a liquid. That's an exothermic reaction. Now don't forget here, I'm not making energy. I'm not making heat. What I'm doing is there is heat and energy inside the gas. It is now being separated from the liquid. So we are producing heat. I can take that reaction and really write it in one. This is what we call an equilibrium reaction. It's like a two-way street. I can take a liquid and add heat to it and make a gas. Then I can take a gas and take heat away and make a liquid. And that'll be important concepts that we use throughout the rest of this year. So, same thing applies to a solid. If I take a solid and heat it, what's it do? It melts. Endothermic. I can take a liquid and I freeze it. We know it turns into a solid. But now wait a second. When we say freeze, what's happening? There's energy or there's heat in the liquid, and if I remove the heat from that chemical, I have now a solid, and that energy has been released. Okay? Now, got a question to ask. When ice freezes, okay, is it an endo or exothermic reaction? And I want you to be able to kind of think that to yourself and explain what's happening to the ice as well as what's happening to the surroundings. It's kind of an interesting conversation that we can have on that. So I want you to kind of think about that, and it'll probably come up someday in class. All right, kind of wrapping up here, the last two things. Le Chatelier's principle. This will be something I just want to introduce now. We'll come back to later. Basically says is if we have things in balance, for example, we have a chemical with some liquid, we have some heat, but we also have a mixture of gas. Okay? Well, if we change something, then what's going to happen is this balance is going to shift and it's going to readjust. Imagine it's a seesaw. Two people are balanced, a third person jumps on one side. Well, now we're out of whack. So what now has to happen? A fourth person has to come to the other side. And so you continually are going back and forth, adding, taking away, so that you can maintain balance between the two sides. And that's a concept we're going to talk a lot about the rest of this year. And then if you take AP Chem, even more. But it's just this concept of if we have something equal and then there's a change, something's got to rebalance itself. Last thing, just two terms. Molar heat of vaporization, molar heat of fusion. Very simply, the energy needed to vaporize a mole of liquid into a gas, and then the energy needed to melt a mole of a solid into a liquid. Okay? These are conversion factors. Molar enthalpy also can stand for molar heat. And all we really do here is we're just treating these like we would molar masses. Right? The number of moles, or the number of grams in 1 mole, the amount of energy in 1 mole, the amount of energy needed. Remember, the units for energy are joules or kilojoules. They really just introduce these topics now, and then they have you do some calculations with water in section 5. Okay? So that's the first part. Again, just looking at some basic phase changes, kind of how they occur, why they occur, and what we're going to do to look at next is phase diagrams, and it's a kind of a graph that can help us answer some questions about some things. So that's what we will do in the next video.